A very good morning, dear students. Welcome to Purnachandra Higher Secondary School. Okay. So, in my previous class, we are discussing about the Biot-Savart's law, the application of Biot-Savart's law, the importance of Biot-Savart's law. This thing we have discussed in our previous class. Okay. So, in this class, we are going to a new part of chapter number, that is your very important chapter number 4. Okay. So, in this part, we are discussing about the Ampere'S law and its application, which is very important from exam point of view. Okay. So, let us first go to the Ampere'S law. So, let us first go to the Ampere'S law. What is Ampere'S law? Let us know. So, Ampere'S law, first of all, we have to put a thing in your mind that as we have discussed in the electrostatics, Gauss law. Okay. So, Gauss law, I told you that Gauss law is applicable only for a closed surface. Very simple. Okay. Similarly, the Ampere'S law is always applicable for a closed loop. Understood? Okay. So, all of you look at the figure. All of you look at the figure. So, what I will take here, I will take a conductor here. This is a conductor AB. This is an infinite conductor. Okay. Just I name it as this. This is a conductor AB. Okay. And if this is a current carrying conductor, it carries a current I. Clear? Okay. So now what are the Ampere'S law states that? The Ampere'S law states that the line integral, listen very carefully, the line integral of magnetic field B, the line integral, that means which type of line integral? A closed line integral. That is the line integral of a magnetic field over a closed surface. That's why it is a closed integral. Listen very carefully. Okay. So the line integral of magnetic field over a closed surface, or over a closed loop, that I can write that is B dot dl. So B dot dl signifies as line integral of magnetic field B. Again I will repeat, line integral of magnetic field B over a closed loop. This is your closed loop. That's why this is the closed integration is equal to the mu 0 times total current enclosed by that surface. Total current enclosed by that loop. So what is the total current enclosed by that loop? 9. So this is my mathematical statement of Ampere'S law. Very simple. Again I will repeat. Okay. That is the line integral. Line integral means integration over a line, but that line must be a closed loop. As you look at the figure, this is the closed loop. Okay. So line integral of magnetic field over a closed loop, that is B dot dl, closed integration over B dot dl, that is equal to the mu 0 times, what is mu 0? Mu 0 is nothing but the permeability. Mu 0 is nothing but the permeability in the free space. So mu 0 times the total current enclosed by that loop. So what is the total current enclosed by that loop? That is I. Okay, so B dot dl, closed integration over B dot dl is equal to mu 0 I. Understood? And one more thing, that closed loop or that closed path, whatever I have taken here, that is called Ampere'S loop. That is called Ampere'S loop. And listen very carefully, as in electrostatic, the Gaussian surface is an imaginary surface. It is not a real one. Similarly, the Ampere'S loop is also not a real loop. It is an imaginary loop. This loop, what is the physical significance of the loop? Now, the physical significance of the Ampere loop, only it is used to calculate the magnetic field. Only to calculate the magnetic field due to this current carrying conductor, straight conductor. Understood all of you? Clear all of you? So this is the mathematical statement of your Ampere'S law, which is nothing but the line integral of magnetic field B over a closed loop. So closed integration over B dot dl is equal to the mu 0 times the total current enclosed by that loop. And what is that loop called? That loop called your Ampere'S loop. Clear? Understood? So this is your Ampere's law. And Ampere's law is always applicable for a closed loop, not for a open loop. Okay, it is always applicable for a closed loop. So next we are moving into, okay, so next we are moving into the application of Ampere's law. Next we are moving into the application of Ampere's law. Okay, so what are the applications of Ampere's law? There are basically three important applications of Ampere's law. What is the first application? The first application to calculate the magnetic field. To calculate the magnetic field due to a straight infinite current carrying conductor. To calculate the magnetic field due to a straight infinite current carrying conductor at some point, any point around it. Clear all of you? This is the first application. We will discuss one by one. Then what is the second application? The second application is that to calculate the magnetic field due to a long infinite solenoid. Due to a long infinite solenoid. This is the second application. Come to the third application. Third application, we have to find out the magnetic field due to a toroid. Okay, so these are the three main applications, and we have discussed one by one, so don't worry about that one. So come to the first application, application number 1. Come to the first application. The first application is your calculation of magnetic field. MF means magnetic field at any point due to a straight infinite current carrying conductor. So this is my first application, application number 1. Okay, so for which what I have to take, what I have to assume, look at the figure, again look at the figure very carefully. So what I have to assume here, I have to assume a long infinite current carrying conductor. This is a long infinite current carrying conductor. Okay, and I will take a point P. Suppose this is my point P. Okay, so what I am going to find out? Now I am going to find out the magnetic field at this point P. Very simple. My aim to find out the magnetic field at the point P. This P point can be anywhere. The P point can be anywhere around the conductor. Very simple. So now what I have to do first? Now first I have to take a loop. So let us take a loop which is passing through the point P. Listen very carefully my words. Let us take a loop which is passing through the point P. Okay, so now what happens? So now this is my what? This is my current carrying conductor. So due to this current carrying conductor, there is a magnetic field arised around it. Okay, so what about from the Biot-Savart's law? So we have to find out what is the direction of magnetic field. Let us find out. So suppose the direction of magnetic field, we can find out the right hand thumb rule. Very simple. So now this thumb, look at very carefully. This thumb gives the direction of electric current, and the curling finger gives the direction of your magnetic field. So now I will place in this manner. In this manner means this is my direction of current, and this is my direction of magnetic field. So direction of magnetic field is in this direction. This is the direction of magnetic field. And everywhere you can calculate. Clear? Okay. Now suppose the total length. Listen very carefully. Suppose the total length of the loop, I can take it as. Suppose the total length of the loop, I will take it as L. So now I cannot find out the magnetic field due to the whole length. So let us take a small element dl. Let us take the small element dl, and the your direction of dl is also in this direction. is also in this direction. Again I will repeat, the magnetic field, just I have got, this is my direction of magnetic field, and I will take a small element dl. I will take small element dl, and the dl direction is also in this direction. That means the magnetic field B and the dl both moves in same direction. So what is the angle between these two? Very simple, 0 degree. So let us find out. So now suppose the distance from this conductor to this point P, let us take it as R. Okay, so now first of all I have to find out the line. Again I will repeat, I have to find out the line integral of magnetic field over a closed loop, and this is my closed loop, imaginary closed loop I have taken, and this is called Ampere'S loop. Just I told you. Okay, so now closed integration over B dot dl is equal to, I have to find out the closed integration over B dot dl over this loop. Okay, so closed integration. Now B dl cos theta. What is the angle between B and dl? Just I have found out here. What is the angle? 0 degree. So that because both are moving in same direction, look at here, B is also moving in this direction, and the dl direction is also in this direction. So that's why the angle between B dl is cos 0 is 1, so that is your B dl. Okay, so that is equal to, let us take the B outside. So now because integration over dl, clear? So that implies so now B integration of dl, I have to integrate the dl with the throw length. So if this is my r, then what is the circumference of this total? 2 pi r. Very simple. So that's why the length or the circumference of the loop is nothing but your 2 pi r. Clear, understood? So dl, integration of dl is L. And what is the length L of the loop? The length L means the circumference of the loop. So what is the circumference? 2 pi r. Okay. So now B dot B into 2 pi r, and this according to Ampere's circuital law, this must be equal to the mu 0 times total current enclosed by the surface. So according to, I have to write here, according to what? According to Ampere's law. According to Ampere's law, what I can write? I can write B into 2 pi r is equal to how much? The mu 0 times the total current enclosed by that path. So what is the total current enclosed by that path? I. So that implies our aim to find out the magnetic field. So magnetic field B is nothing but mu 0 I divided by 2 pi r. Which is very important. Listen very carefully. So this is my expression of magnetic field. Again I will repeat. Suppose I will give it in equation number 1. So the equation number 1 signifies the magnetic field due to a straight current carrying conductor at some point P. The expression is B equal to mu 0 by 2 pi r. And what is the direction? How will get the direction of B? Because B is not only having some magnitude but also having some direction. So that's why the B direction of B, just I told you the direction of B or magnetic field can be found out using the what? Right hand thumb rule. Clear? So this is my direction. So this is my direction of B. Tangent to this loop. Understood? So this is the expression B is equal to mu 0 by 2 pi r, which is very important from the derivation point of view, and so also from the problem point of view. Clear? All of you clear? So this is how we can calculate, or the first application, that is the magnetic field at any point due to a straight infinite current carrying conductor. Understood all of you? Clear? So this is my first application. Then come to, let us move into the second application. Let us move into our second application. So second application number 2 is your solenoid. Okay, is your solenoid. Okay, so now this is the graphical or structural and some of the graphical representation or structural representation of a solenoid. So what is a solenoid? First of all, let us know. So solenoid is nothing but a helical structure. Okay, just like this. So this is a helical structure. That means a wire or a coil is wounded. Which type of coil or which type of wire? Insulated wire. Listen very carefully. So this wire is an insulated wire which is wounded over which is wounded, and each turn are placed very close to each other. Understood? Again I will repeat. So solenoid is nothing but a helical structure in which a wire or a loop, okay, the wire is closely wounded. Which type of wire? Insulated wire is closely wounded, okay, over a surface. Which type of surface? The cylindrical surface. Clear? So that's why this type of structural representation you will find for a solenoid. Look at this. So this is your coil. This is the coil of your solenoid, which looks like a helix. These loops are actually very close to each other. As they are very close, so the magnetic field is strong. Okay. If they are apart, then the magnetic field becomes weak. So now these are the magnetic field lines. Again I will repeat. These are the magnetic field lines. Okay, which are generating from here and ending or terminating here. Similarly, look at here. Similarly, this is the direction. This is emerging. Okay. This is the direction of your what? The magnetic field. This is the direction of your magnetic field, which is very important. Clear? So these are These are the loops. Look at this carefully. These are the loops which I have just marked here. These are the loops. Loop number 1. This is loop number 2. This is loop number 3. This is loop number 4, and so on. So around this loop, magnetic field is created just like that. And these loops are called Ampere loops, just I have discussed. Okay. So now this is a helical structure where the wires are wounded very close to each other. Spaced very close to each other. Okay. So what is our aim? Now our aim to find out the magnetic field due to this solenoid. Our aim to find out the magnetic field due to this type of solenoid structure. But before there a question in your mind, sir, how could you know that this is entering here and this is exiting here? Okay, so this direction, or actually a very important point is that when the solenoid conducting some current, look at here, these arrows here, this is the flow of current IE. Similarly, here also these are the current flow. These are the current flow, okay, which are flowing inside the solenoid, the loop of the solenoid. This is the current I. So when the current is flowing in the loop or in the solenoid, then magnetic field lines are produced. Clear? Okay. So now remember one thing: when the current is flowing inside a solenoid, then the solenoid behaves like what? Behaves like a bar magnet. Okay, so bar magnet means, all of you know, bar magnets is the bar shaped magnet which is having two poles. One is north pole, one is south pole. So similarly, the solenoid is having also polarity, is having also a north pole and having also a south pole. Clear? So that means, how could you know that this is a north pole or this is a south pole? So let us discuss. Let us discuss. Okay, so look at it. Look at it. When we look into one end, listen very carefully. When we look into one end of the solenoid, suppose I look it from here. You can also look it from here, it is up to you. But suppose I am looking at one end of the solenoid. If the current flows in which direction? Clockwise direction. This is your clockwise direction. So when the current flowing in this side, clockwise direction, then I will assume this side as which pole? South pole. Clear, all of you? Okay, so again I'll repeat, when the current flowing in this loop from this side, then this pole is assumed to be as south pole. And when the current is flowing in anti-clockwise manner, then it is taken as north pole. So in this way you can find out the polarity of a solenoid. When the current flowing, if you look into one side of the solenoid, one end of the solenoid, then if the current flowing is in clockwise direction, then this side of this solenoid is taken as south pole. If the current is flowing in anti-clockwise direction, then this end or this side taken as north pole. If this is south pole, then obviously the other part is a north pole, and if it is north pole, the other part is a south pole, vice versa. Clear, all of you? So this is how you can know. Current flowing is clockwise manner, you have taken as south pole. Current flowing in anti-clockwise manner, you have taken as north pole. Okay, so in this way you can find out the polarity of a solenoid. Okay, so as we have known, suppose this is your bar magnet. So in the bar magnet, suppose this is your north pole, this south pole, then the magnetic field lines are arising from the north pole, ending at the south pole. Clear? Ending at the south pole. This is very important. This is very, very important. So always magnetic field lines is generating from which pole? North pole, ending at south pole. Okay, so now let us find out the magnetic field due to this solenoid. So for this, what I will do, now I have to take similar process. I have to take Amperian loop. So let us take Amperian loop. So let us take, I will take a Amperian loop. This is my Amperian loop, which is an imaginary loop. So let us name it A, B, C, D. Clear? And let us take the length of the solenoid becomes L. Length of the solenoid becomes L. So now this is my Amperian loop. Again I will repeat. This is my Amperian loop. This Amperian loop is an imaginary loop which is only taken for the calculation purpose. Calculation of what? Calculation of magnetic field. Okay. So now that means now this loop has how many sides? AB, BC, CD and AD. So every part is nothing but a section. Okay. So let us first find out closed integration of B dot dl. This is our first point. We have to find out closed integration over B dot dl. But closed integration means closed path. So this path contains how many sections? AB, BC, CD and AD. So let us find out for each section. So that implies the first section. First section suppose AB. AB section. Okay. So AB section B dot dl plus next is your B C section. Again B dot dl, then C D section B dot dl, and come to the last one, that is D A section integration B dot dl. Understood? Clear all of you? So these are the sections where we have to going to find out B dot dl. So now that implies so closed integration over B dot dl is equal to 1 by 1. Let us find out. So AB, look at it, very listen carefully. So when we will move into, starting from A, we will go to the B. Then in this is your dl. Which is dl? AB is nothing but the dl. This is the section. And the magnetic field is in this direction. That means AB direction and magnetic field direction. Again I will repeat. AB direction and magnetic field direction. Both are in same direction. This is the direction of AB and this is also the direction of magnetic field. Look at here, this is the direction of magnetic. Both are in the same direction. So what is the angle between these two? 0 degree. So that's why I have to write from A to B, B dl cos 0 degree. Clear? Plus come to here, B to C. Then look at here. B to C, BC is your dl. And this is my direction of magnetic field. Again I repeat. This is the direction of magnetic field. This is my dl. So what is the angle between these two? 90 degree. B, magnetic field B, and this is my dl. So what is the direction of magnetic field and dl? 90 degree. So what I can write here? Now BC, that is B dl cos 90. Okay. Then plus come to CD. CD. Look at that, very important. The CD section. The CD section of the loop is present outside the solenoid. Present outside the solenoid. That's why there is no magnetic field exists. That's why there is no magnetic field exists at outside the solenoid. So for CD section, the magnetic field B becomes 0. Totally 0. Again I will repeat. For the CD section which is present outside the solenoid. Okay. Fully outside the solenoid. That's why there is no magnetic field exists in CD. So that is 0. Now plus again D to A, same process. That is integration D to A. That is B dl cos 90. Why? Because the dA is your dl. This is your magnetic field angle 90 degree. So now that is equal to all these value becomes 0. Cos 90 is 0, 0. Cos 90 is 0. So only left here. So that is integration B dl. Integration B dl. Understood all of you? Clear? So now, so that is equal to B I have taken outside. So integration over dl. So integration of dl is nothing but your L. Because the length of the solenoid becomes L. Understood? Understood all of you? Okay. So now, so BDL this much. B dot dl is equal to this much. Clear? So now this, according to Ampere's law, listen very carefully. According to Ampere's law, this must be compared with, or this must be equal to mu 0 times of the total current enclosed by the solvent. So what is the total current enclosed by the loop? I. So let us compare. So by comparing, so now applying Ampere's law, so this is my BL is equal to mu 0 I, but question is that this is mu 0 I for how many loops? One loop, but there are n number of loops. We don't know how many loops are there. There are n number of loops. So that's why I have to write it here, mu 0 ni. What I can write? Mu 0 ni, where n is the number of turns in the loop. Okay, so mu 0 ni. Why? Because there are n number of turns in the loop. Clear? So that's why that implies, so magnetic field B is mu 0 ni divided by L. Mu 0 ni divided by L. So this is the expression of magnetic field due to a long solenoid. Understood? And this can be expressed also mu 0 small ni. Listen very carefully. Mu 0 small ni. Why? Because small n is equal to capital N divided by L. That is number of turns per unit length. Number of turns per unit length. So n is nothing but small n. Small n specifically is nothing but number of turns per unit length of the solenoid. Again I will repeat. What is small n? The small n is the number of turns divided by length. Number of turns per unit length is the small n. So I can represent in this manner, or I can also represent in this manner. Okay, so this is the expression of your magnetic field due to a long solenoid. Okay, and one very important point I have just proved that inside the, listen very carefully, inside the solenoid the magnetic field lines becomes parallel. So that's why inside it the magnetic field becomes uniform. Number one. Number two, outside the solenoid the magnetic field becomes zero. There is no presence of magnetic field. Understood? And this is the expression of magnetic field due to this long solenoid. So come to our third application, that is your toroid. We have discussed two applications of your Ampere's law. So come to the third application, this is your toroid, which is very similar to your solenoid. Clear? So in the solenoid, it is arranged in helical structure, but it is a cylindrical manner, in a straight line manner, cylindrical manner. But if that solenoid is curved to a circular one, that means look at the figure all of you. Okay, so what happens in this figure? The coil is wounded over a which type of structure? A circularly cylindrical structure. With this type of shape is called donut shape. Which type of shape is called donut? D-O-U-G-H-N-O-T. This is called donut shape. Okay, so donut shape. So when the solenoid is shaped or is arranged in a circularly cylindrical like structure, just like this, okay, then that type of structure is called toroid. Clear? That type of structure is called toroid. And the same aim here also we have to find out the magnetic field at some point P, which is present at a distance r from the center. Suppose I will take as this the total the cylinder is suppose a circular path, very simple. Then in the circular path the dotted structure is an Amperian loop. So if this is an Amperian loop, then in this Amperian loop, suppose this is your center of the loop, this is the radius, and you have to find out the magnetic field at point P. Very simple. Clear? So now similar manner, first we have to find out line integration over B dot dl. Okay, so when just look at it, so the current is going inside it, current is out from it, current going inside it, the coil at one end, coming from it at other end, and it is wounded over a circularly cylindrical structure. This is called donut shape. Okay, so when we will visualize it, then at every loop, the magnetic field becomes a tangent to the loop. Listen very carefully. A tangent to this Amperian loop. Okay, so now that means the same point, if it is tangent, then the angle between DL and B also in the same direction. So B dot DL is nothing but integration. Let us take the B outside. Okay, so first of all, as they are in same direction, so B dot DL, B dl cos theta, theta becomes 0 degree, so cos 0 is 1, so this is B dl. So let us take it outside, so integration of dl, very simple. Okay, close integration. So integration of dl, that means the circumference of the loop. Again, so circumference of the loop means that each circumference is 2 pi r, so B into 2 pi r. Okay, so now according to Ampere's law, this BDL must be equal to the mu 0 times total current enclosed by that loop. Okay, so in that loop, how many turns? N number of turns. So mu 0 I and n number of turns are there, as we have done in the solenoid. So that implies B is equal to mu 0 Ni 2 pi r. So this is my magnetic field. Again I repeat, this is my magnetic field due to a toroid at any point on the toroid. On the toroid, look at that. The point P is present on the toroid. Okay. So B is equal to mu 0 Ni by 2 pi r, where n is the number of turns in the loop, and I can also write mu 0 Ni as we have done in the solenoid, where the small n is nothing but capital N divided by 2 pi r. Okay, that means the number of turns per unit length. Unit length, what is the length? That is the circumference 2 pi r. So n is the number of n, small n is the number of turns per unit length of the toroid. Clear? Okay. So there also mu 0 small n, here also mu 0 small n. But the difference is that this is mu 0 n by 2 pi r is a circular manner, but there is a straight cylindrical structure which is a solenoid. Clear? So this is the third application. You have to find out in this way the magnetic field of a toroid. Clear? Okay. So this is for this day. We have discussed all the three applications of your Ampere's law. Okay. Have a good day. Thank you so much.